Hello everyone, this is Dr. Jianfu from Hofstra University. It is my great pleasure to present IZPR, the Instant Zero Knowledge Proof of Reserve Protocol, which was recently presented at the Coordinated Decentralized Finance Workshop 2024. This is joint work with Mayne, who's at KN0x1Y, and also my students, Trevor, Nirso, Diego, and Alvin. So in the last decade, we have witnessed numerous scandals about cryptocurrencies. While cryptocurrency platforms may die of many reasons, attacks and exploits remain as the single most dangerous threat to major cryptocurrencies. And we can see that millions of assets could evaporate just through one hacking transaction in seconds. Now we are coming back to the million-dollar question for centuries. That is, how can we prove the solvency of a financial organization in zero knowledge? All right, so essentially we want to prove that the asset of an organization is greater than its liabilities. So in the age of cryptocurrency, certainly there are several desired system security properties that we would like to achieve. So the first property is zero knowledge property. So essentially when we try to prove the solvency, we want to make sure that no details of the accounts owned by the finance organization will be leaked. The second property is called the instant property. That is, we would like to provide the asset proof in high frequency, for example, every second. So compared with the current frequency of financial disclosure policies by most financial organizations, this apparently would be very appealing to small investors because any cybersecurity incidents related to these cryptocurrency platforms would be then immediately visible to all. So the third property we would like to achieve would be that the proof system should be systematic, automatic, avoid human efforts as much as possible. The proof should be small and easy to verify. And lastly, but most importantly, we also would like to make sure that the proof generation is secure and safe. That is, when we generate the proof, we actually do not need to take out the secret keys of wallet addresses from cold wallets for generating the proof. So this might be seeming counterintuitive, but we will show later in this talk that it can be actually achieved using our system. So here in this paper, we assume that the liability proof is available. So typical examples such as DAPL and DAPL Plus have been deployed in real systems such as Binance. And its basic idea is to build a Merkle tree that accumulates all liabilities, and then each customer can get an individual ownership proof. So it's basically like a Merkle tree pass proof. So the focus of this paper is to solve the IZPR problem. That is how we can prove the asset of an organization in zero knowledge and instantly. And we name the project as IZPR. So before we talk about our own work, we would like to briefly survey the state of the art of the related work. So zero knowledge proof of asset first appears in a paper called Provisions, which appeared in CCS 2015. So the system leverages the Schnorr-style Sigma protocols to prove the ownership of a set of BTC addresses. Notice that it does not provide a second proof, and the work needed by both the prover and verifier would be linear in the size of the anonymity set. So for instance, for an anonymity set size of 500,000 BTC addresses, it takes about 1 hour for prover to prove the work and about 1 hour for the verifier to verify the proof. However, we know that nowadays we have about 80 million BTC addresses. So to achieve a full anonymity, provisions would need about 160 hours of computing time, and this is about 1 week of computing time. So another example is to use ZK snark based approach. So this approach provides succinct proof. However, the concrete proof of cost is high. So for example, for pure ZK snark approach to prove the ownership of one BTC address, one would need about 4 million RNCS constraints. And we know that for the state-of-the-art, typical proof of time for 1 million RNCS constraints would need about 10 to 100 seconds of computing time. So if an organization has a lot of wallet addresses, then the proof of cost will be very expensive. The most recent work is Godzilla, which uses the MPC in the head approach. So the multi-party computing in the head approach provides very fast prover efficiency. But even like that, it does not meet our requirement for an instant prover. So for example, as shown in the Godzilla paper, it does achieve the anonymity for an entire 80 million of BTC addresses. However, it still needs 1 minute of proof of time for the ownership of one wallet address. So again, if an organization has a lot of wallet addresses in its asset, the proof of cost will be very expensive. So in summary, none of the related work so far is concretely efficient to support an instant asset proof. Like we would like the asset proof to be provided at a frequency of 1 second. So then we will talk about in our work how we are able to accomplish the goal. So how is this work different? The great advantage of this framework is that we support an unlimited size of anonymity set. Our proof of cost does not depend on its size. And in fact, our proof of cost does not depend on the owner set as well. So our proof scheme is safer. So there is no need to take out secret keys from cold wallet for every instant proof. And in practice, our concrete performance is great. With a $5 per hour Google Cloud server, we are able to support 1,024 transactions. Recall that BTC has a throughput of 7 transactions per second. Visa Network works at 2,000 transactions per second. And New York Stock Exchange works at 14,000 transactions per second. So with a very low cost Google Cloud server, we can already support the performance of the throughput of Visa Network. So we now talk about the main idea of our system. So the key idea is that the ownership of wallet addresses only needs to be done once. So we can have a bootstrap stage first. So in a bootstrap stage, an organization can pre-compute all the secret keys for all the wallet addresses that it would need to use in the future first. So store them securely in a cold wallet database first, and then provide the following information. So first we'll have a commitment to the vector of all addresses, so that these addresses are hiding behind the Peterson commitment. And the commitment to the initial asset value, and then a zero knowledge proof, which shows that, well, the organization does know the secret key which generates these BTC addresses and the correctness of the initial asset. So recall that the size of these commitments is very small because each commitment is only a group element. And usually for ZK snark system, the zero knowledge proof is also very small, usually less than 1,000 bytes. Then we will perform the instant proof at each transaction epoch. So for example, for BTC, based on the public blockchain information, the account balance change for each wallet address is actually publicly visible. All right, but here we only want to sum up the balance change for those accounts that are owned by the organization. So for example, this and this address belong to the asset. We only want to sum up the changes for 100 and 200. So the prover first provide a secret Boolean vector for each BTC address in the transaction records, which indicates whether this address is belonging to the asset of the organization or not. And then the prover provides a Peterson vector commitment for the secret Boolean vector. And recall that it's only one group element. And the prover also provides a commitment to the total balance change. In this case, is 100 plus 200 is 300. And then the prover provides the instant zero knowledge proof, which shows that the sum of the entries which has the Boolean value 1 set is indeed the value that is hiding behind the commitment of the total change. And now, because all commitments are Peterson-like or its variations, they are homomorphic. So the commitment to the total asset can be simply accomplished by adding up two group elements. Now, we will now present some technical details at high level, and the paper has the formal presentation of all the protocols and cryptographic constructions. All right, so our starting point is a lookup argument called CU protocol. So in the CU protocol, we have a public lookup table T, and the prover has a secret query table small t. And the argument tries to establish the fact that all the entries appear in the query table T belongs to the lookup table big T. The beauty of the CU protocol is that since the lookup table is to be reused, so the prover can actually perform a pre-processing step. So then for each proof, the prover only needs to pay a linear number of group operations, and the verification cost is constant. So what does that imply? This implies that the prover cost is independent of the lookup table. So in our application context, this means that as long as the financial organization pays a one-time pre-processing cost in the bootstrap stage, its BTC address set can be arbitrarily large, and at runtime, the prover cost is not affected by its asset size, but the platform throughput. Note that the CU protocol itself is not zero knowledge, and to see why, consider how a commitment is generated for a vector table T. So first, we can easily define a univariate polynomial based on Lagrange-based polynomials, which encodes each element of the vector T. And then given a KZG polynomial commitment keys, its sequence of group elements represents the power series of some trapdoor S. And then the KZG commitment for the polynomial T of X can be computed and generates a single group element. So then for the CU particle, the proof involves the proof for the relation between several committed polynomials. So how is this proved? The verifier could simply raise a random challenge R, and then the prover could show using the KCG proof that at this random point R, the polynomial hiding behind the first commitment evaluates to a point T, and similarly, we got three values T, Y, Z as the evaluation of the three hiding polynomials. And then we simply verified the relation of this lowercase T, Y, Z here. Now, unfortunately, notice that a single point of evaluation of a hidden polynomial in KZG still leaks information about these polynomials. So what we do here is that, in fact, we will not even disclose these values T, Y, Z. We hide them behind the Peterson commitments so that the verifier cannot infer even the leaked point values. And then we use Schnorr style sigma protocols to reason about the relation between these hidden values so that we retain the full zero knowledge. Then, from the zero knowledge CU particle, we can define a batched range proof. That is, given the commitment of a vector of numbers, we can prove that all of them belong to a certain range, like all of them are 20-bit unsigned integers. Based on that, we can have batched range proof for 160-bit numbers. As you can see, this can be easily implemented using 8 zero-knowledge range proofs for 20-bit numbers. And as you know, 160-bit is the width of BTC addresses. Then based on the range proof, we are able to prove that an element does not belong to a lookup table. Do you see the idea? Given that a simple lookup table of 4 elements, note that they are already sorted. How do we prove that 250 does not belong to this table? We simply prove that 200 and 300 in the hiding form belong to the lookup table, and then prove that 250 sits in between 200 and 300. So this proves that 250 does not belong to the lookup table. Then, based on the negative lookup argument, we can have a zero knowledge positive negative lookup argument. Recall that it allows us to support a Boolean vector to indicate that if an account belongs to the asset or not. And finally, with some additional polynomial related zero knowledge proof technique, we eventually got the IZPR particle. So we have fully implemented the IZPR particle, and we evaluated at our Google Cloud Computing C2D instance. It has 56 cores and runs at $5 per hour. The maximum performance of the system is achieved at 32 threads. So the proof of cost is 0.935 seconds for 2,000 account updates, assuming that each transaction takes 2 updates. So it is equivalent to supporting 1,024 transactions per second. The verified cost is very low, and the proof size is 3.4 kilobytes. This slide shows you the scalability of the system, and you can see that the scalability is very good. As we discussed earlier, the CU lookup protocol has linear proof vector complexity. So Based on it, all the other components of our system is also linear for the proof of cost. In addition, when we increase the number of the threads, you can see that the performance also scales very well. The project is currently implemented using the standard Rust multi-threading feature, but with some engineering efforts, we can integrate distributed computing such as OpenMPI framework to further boost the performance of the system. So far, we have not talked about the bootstrap process. Stan from KN0x1Y has provided a concrete implementation, and we are merging our protocol with his work. So for the bootstrap process, an exchange would like to give evidence that they own a set of blockchain accounts without exposing which ones. They would also like to commit to the sum of the balances of these accounts without revealing the said sum. And the only way that they can show ownership of an account is by providing a digital signature, and they cannot show the private keys explicitly. So here, a ZK snark is used to first validate each signature and verify that it corresponds to exactly one address in the anonymity set. And second, it is used to construct a Patterson commitment to the sum of the balance of the accumulated addresses. So here, notice that the anonymity set is are represented as a Merkle tree, and the membership is checked using Merkle tree passproofs. So this allows the anonymity set to be very large, and a set of 10 million addresses can be easily manageable. In practice, the actual size of the ZK snark is limited first by the size of the circuit needed for just approving a single digital signature. And also, this is also limited by the number of the approval keys available. So here, the idea is to have separate snarks for the ECDSA verification and anonymity set membership check. So Stan actually uses the multiple layer ZK snark system, and Grow16 is used as the proving system because it has the smallest proof size and verification circuit, which are currently known so far. So for the bootstrap stage, when we use the ZK snark system by Stan, for one single wallet address digital signature, the current implementation takes about 3 minutes for proof generation, whereas the circuit for just one single digital signature is large. For 6,000 signatures, wallet addresses, it runs about 150 hours on Amazon Web Service, costing about a little bit less than $900 for 6,000 wallet addresses. That is for the bootstrap cost. So in conclusion, we have presented an instant zero-knowledge asset proof based on the pre-processing lookup argument. Its proof of cost is independent of the anonymity set size, and the scheme has practical concrete performance. What's more, the scheme does not need the secret keys when generating instant proofs, and also it is non-intrusive, which means that the scheme does not need changes on the blockchain platform itself. Several cryptographic constructions are of independent interest. For example, we developed a zero-knowledge version of the CU protocol, but we recently found that a concurrent work named the CQ++ which even provides better concrete performance. So if our zk-CQ is replaced by CQ++, we can actually further improve the performance of the scene for about 1 time. So for the future directions, we plan to address the asset protocols for full privacy-preserving cryptocurrency, such as zero calling and zero cash. A second protocol is already available. It is also built upon the lookup argument. So this is the end of our. We would welcome any questions.